Okay, so let's talk about our next topic here, topic 6. Before I get to some new formulas we're going to add to our list, why don't I do a little bit of a review of some formulas we've learned so far. I believe we have 6 formulas on your list, and ideally these should be on that formula sheet that I gave you at the beginning of the year, but I believe that the printer really screwed some of them up, so feel free to write them on your formula sheet. Here's the ones we've learned so far. Here's the first one. Velocity or speed is equal to a change in your distance or displacement over a change in time. And if I can put a little note next to this one here, this formula is only appropriate in a very specific situation. Some of you have already kind of learned this because you maybe got a question wrong. You can only use this formula when you have something called uniform motion. What the heck does uniform motion mean? It's always going the same speed. Well done. Yeah. So, hi. No. I do, yes. You need that one? No, it's not good. I think I probably bugged your class a few times, so. Okay. So that first formula here, V equals D over T, you can only use it if the speed is not going to change. Can we use that formula then when we race our Hot Wheels? No, because they're slowing down. Can we use this formula tomorrow when Brady drops stuff off the roof? No, because stuff's going to be speeding up. So be very careful when you utilize that formula. It's very rare that you get to use it. We start with it because it's kind of an easy one, but it's not that common that we use it because it really has a very specific condition to it. Okay. Next formula, acceleration is your change in velocity over change in time. If you're speeding up or slowing down, we can calculate that speeding upness. Okay. So that's formula 2. Along with those 2 formulas, we learned a few other ones. These are the ones that we're going to practice in our 2 labs. D equals VFT minus 1/2 AT squared. That's the formula we utilized in our first lab. And hopefully, by using this formula, some of you are able to notice that there's the negative that's sitting right here. And the reason why this negative kind of made sense is that when we finished solving for acceleration, it made it a negative acceleration, which is good because it's supposed to slow down. What we're going to utilize tomorrow then is this formula, D equals VIT plus 1/2 AT squared. So I want to talk a bit more about tomorrow's lab again. In terms of what we're going to do, we're going to try to calculate some values, and we can utilize this formula. For example, this D right here, we can measure the distance that the object will fall off the roof, right? We'll just use a tape measure. We can calculate time, because we'll just measure it by hand. I don't know that it's going to be accurate or not, but we can try to measure it. And we can also talk about the initial velocity, because what's going to happen is Caretaker Brady, he's going to drop something off the roof. If he literally holds it out above the, over the edge and lets go, what's the initial velocity when you just drop something? Is it moving right now? No, I'm just holding this here, right? So when I let go of it, it actually has no initial velocity. In a similar way to how we can have no final velocity, you can also have something start at rest. So, anyways, that's the formula we're going to utilize tomorrow. And we've been using it otherwise. And then we've learned 2 other formulas, I believe. One is, it's a very basic formula. It's that work occurs because of a change in energy. When you change a state of energy, you have work. It's kind of a silly formula, honestly. But what I need you guys to know is that if I give you an amount of work that you do, I've also told you how much energy you've used. And then the last formula we've learned was this one here. Work is equal to a force times a distance. And this one, I think a lot of kids kind of get it, but they disagree. They struggle with the difference between work and force. Okay? Most kids, I think you understand a force. A force is where you're exerting some sort of effort, and you're pushing or you're pulling, and like if you're an athlete, if you're hitting something, like you're gonna get sweaty over time because like you're exerting yourself. Does that make sense? But for it to technically be considered work, that force has to occur over a distance. So if you just push against the wall and the wall never moves, technically you're not doing any work. But like, are you using force? Yeah. Okay. But force and work are kind of independent of each other. Okay. What we're going to do today then is we're going to learn 3 new formulas. Okay. I'm going to show you a formula for force. And these are on future slides, but I'll show you them right now. I'm going to show you one formula for calculating a force. And sometimes we put a little letter down in the bottom corner here. You know how there's like a little F right here for velocity F and velocity I? F and I stand for final initial, right? We're going to put a little letter sometimes right here called FG, just to let us know which force we're talking about. And this is specifically going to be for gravity. We're going to talk about how gravity is a force that causes things to fall. Okay? And the formula we're going to learn today is it's M times G. And I'll explain these ones as I go through my lesson, but that's a new one on our list. And then we're going to talk about some formulas for energy. And again, I'm going to have a couple of little like smaller subscripts down here. I've got one that's going to go E, and we usually go with G. And this is going to be the energy that you get due to gravity. And the formula is very similar. It's mg delta H. And again, I'll talk about those as we get to them. So this will be the force due to gravity, and this will be the energy due to gravity. Similar, but different concepts. And the last formula we're going to learn about today is going to be E with a little K in the corner. And this is energy kinetic. And if you guys recall the term kinetic energy, it basically refers to like something that is moving. Okay, there's energy in the form of, say, light and sound and heat and nuclear energy, all those energies. We're going to specifically talk about objects that have kinetic energy, which means these are objects that are moving, things that have been thrown or dropped or, I don't know, something like that. So anyways, this formula goes like this. It's 1/2 of mv squared. And I'm going to go draw that blind because that's in my eyes. I can't imagine what it's like for you guys here. Is that better? It's not shining in your face? Okay. Okay, so let me start my notes here then. Pardon me. We're going to talk about some different energies today. Before I get to the formulas that I mentioned, I want to talk about some bolded, underlined words here. The term is called potential energy. If it's not a kinetic energy, which is the energy of something that's like, say, in motion, it's probably a potential energy, meaning it's an energy that's like waiting to occur. It's going to happen, but later. Okay. Often we'll talk about the idea of the stored position or the released position, where you have some sort of item. The best example I can think of is like, let's say it's a slingshot. Okay. You guys will have to maybe like watch me for a second here as I demonstrate with my hands. Imagine I have a slingshot in this hand right here, and I'm going to pull the slingshot back to here. And I'm just waiting to let go. Can you guys agree that like this is the stored position? And as soon as I let go, it's going to go and fling forward. That would be the released position, right? As I'm pulling back right now, is there energy that's like actively happening? Well, not yet, right? Which is why it has the potential to react. And as soon as I do let go, that potential will get converted into kinetic energy. And that's what we're going to be talking about over the next few days, is the idea of something that has the ability to move, it's just not moving yet, and something that is now moving. That's the difference between a stored and a released position. Okay. Let me give you an example of a form of potential energy. Gravitational. Let's say that this snowboarder right here is just finished doing a half pipe, and he's gone all the way up like this, and he's come all the way up to here, and he's at like the peak of his jump, and he's about to start going back down again. So he's about to start going back down again. But for a brief moment in time, imagine that he's gone all the way up here, and he's like just hovering in the air for that split second. He's actually not moving, so he has no motion energy at that second. But he has the potential to, or she has the potential to be able to come back down, right? And what's going to cause this athlete to come back down is that there's potential due to gravity, right? The higher you are above the surface of the earth, the more, I don't know, energy you're going to gain when you fall. Imagine that I were to jump off of a desk in this classroom, or I were to jump, hypothetically, off of the roof. Which one's going to be more dangerous to me? Well, obviously the roof, right? But why? Well, because I have more energy when I'm on top of the roof, right? Why do I have more energy? Because I'm higher up. Does that make sense? Right? So the further higher up you are above the Earth's surface, the more energy you would have, right? So Here's another example of potential energy. It's the elastic slingshot example, right? You have to do some work to give it that energy. The work is by applying a force over a distance to pull the slingshot back. But when you do that work, you give it potential energy, so that when you pull it back, you can then let it go, and it's going to go flinging forward with potential energy. There's another example. There are more examples of potential energy, not that we're going to use formulas for them yet. If you take physics 20 and physics 30, at some point, yes, you will, but not yet. But here are two more. One is chemical potential energy, and that's where chemicals actually have bonds that can either release or gain energy through chemical reactions. We actually know this concept from our last unit. We call these things exothermic. Do you guys recall that word? Exothermic reactions are reactions where it gives off energy, because energy is literally released. Where does that magical energy just show up from? Well, it's the bonds in the chemicals that are being broken. If you were to burn a piece of firewood, the theory used to be, if you guys recall this word, it used to be called the phlogiston theory, and it was very wrong. But they had this belief that like certain chemicals had like just this random heat trapped inside, waiting to escape. And now we know that it's actually energy in the form of bonds that are being broken. The last one we're going to talk about here, not that I've got formulas for it, but is nuclear potential. It's actually possible for us to make nuclear bombs or nuclear chemical reactors, right? We use them for power plants. And similar sort of thing there. There is energy inside the nucleus of an atom. And some kids, they sometimes ask, Chris, why is there energy in the nucleus? And I don't mind explaining this because I think I can do that well. You guys remember the nucleus, how we put a lot of protons in a nucleus? And sometimes there's some neutrons in there as well. And then we surround it with electrons around it. Let's talk about the nucleus for a second here. If the nucleus is all positive and neutrons, what do positive things do nearby other positive objects? Do you guys know? They want to repel each other. Yeah, there's a concept in physics and chemistry where if you have the same charge, or maybe even the same like magnetism, you want to repel each other. Like north magnets repel other north magnets. All these positive charges in the nucleus want to repel each other, but they don't. And it's due to something called a strong nuclear force, which we learned about in physics 30. But I think you guys get the idea that all these neutrons right here, they should want to explode, because all these positives don't want to be beside each other. And due to the strong nuclear force is like a glue that keeps them all stuck together. Right? Imagine that you went to the store, you bought a whole bunch of magnets, and you tried to force the magnets together, but like you had the opposite ends near each other, and so you can't get them together. But like you found a way by supergluing it. But let's say eventually the superglue broke. The magnets would just all of a sudden go and split apart, right? That's what happens in a nuclear reaction. Does that make sense? So if you find that interesting, it's physics 30 we talk about that. So same concept though. Until it actually explodes, there is potential for it to. Which is kind of cool. Okay, so let's talk about the one force and energy though that we're going to do in physics 10. Okay, we're really starting off basic. We're only going to talk about one force and one type of energy. We're going to talk about stuff that has to do with gravity, which is good because gravity is an easy force for us to do tests on, which is why tomorrow we're going to go drop stuff off the roof. Because why is it falling off the roof? Because of gravity, right? So let's talk about the idea behind it. Gravity is a property that applies to any object that has mass. Okay? If it weighs something, and it is matter basically, masses attract each other. Now, technically, all objects have a gravitational force between them. Okay? For example, this is maybe kind of silly, but this stapler right here and this calculator, there is actually gravity acting between these two forces. Which some people, they don't believe at first because they're like, what? Because these two things are not like sucking in towards each other. The reason why, though, is that their masses are very small. Okay? Gravity is based on how heavy something is. And so if things are relatively light, we don't really notice gravity that much. Why do we notice gravity on Earth then? Because Earth is massive. That's why. Is there gravity on the moon? There is, yeah. But if you've ever seen like pictures or heard of like astronauts walking on the moon, they can kind of bounce a little bit more, right? When Neil Armstrong went to the moon, like they bounce all the time, right? Why? Well, because the moon isn't as big as the Earth, and that's why there's less gravity there. That's basically the concept. If you were to try to go to a bigger planet than Earth, not that you could really go to the sun, because the sun would burn you up due to heat, but hypothetically, let's say that you could go to the sun, you would not survive because gravity would be so strong on that planet that you would literally become crushed like a pop can that someone like goes like crushed, like collapses on itself. We're pretty fortunate actually. Earth is like just the right size that gravity is not too strong and not too weak. Because if it was too weak, we might go flying off the surface of the moon. Right? That's actually happened before. You send a rover to the moon. It's supposed to land on the moon. It accidentally hits the moon too much. It bounces back up, and there's not enough gravity, and it just bounces back into outer space. Whereas if you had the exact same thing on the sun or Jupiter or Saturn, for example, you'd get crushed. Gravity would just collapse you on yourself. So, anyways, here's what you guys need to know. On Earth, then, assuming that there's not a lot of air friction, we actually know how strong gravity is, and we have a number attached to it, which we're going to calculate in our lab, actually. That's our hope. We call it G, which makes sense. G is literally like for gravity. And this is how fast gravity accelerates things. It's at a rate of 9.81 meters per second. And that seems to always hold true. It doesn't matter what object it is. This is how fast it accelerates. So we use the letter G to reference this. And I want to go back now. Actually, I'll just go forward, I think, to the formula we're going to use. Here's the formula. F little g. This is the force caused by gravity. And if you want to figure out how much force gravity applies, there's really two factors. I've already talked about this first one, though. Mass. What is the force of gravity between me and my calculator? Not a lot. Because both me and my calculator are relatively small. Right? But mass does seem to matter because Earth gives us gravity. Right? And Earth is big. Okay. Now, this m right here, though, it is the mass of like the object, though that is like being, that maybe I'll say that it's falling. Let's say that. That's the mass of the object that's falling. Let me give you an example. Let's say that you were to drop a tennis ball on your foot, or you were to drop a bowling ball on your foot. Which one would hurt more? Bowling ball. Why? Because it weighs more. The force of gravity is going to affect it more because it is heavier, right? The second thing, though, is this number right here. If you're on Earth, things accelerate at 9.81 meters per second squared. That's what we seem to have calculated it as. Okay. By the way, on the moon, it's about 1.62 meters per second squared, give or take. Not that I need you guys to know the moon's value, because we're not going to do calculations on the moon, because, well, we don't live there. But just for a frame of reference, things accelerate on Earth much faster than they do on the moon. Which makes sense. That's why it's so bouncy on the moon. Okay, last thing I want to talk about before we try some examples on this formula later. What are the units that we use? Okay, G is an acceleration. So acceleration is measured in meters per second squared. M is mass. That's how heavy something is. We always weigh things in kilograms. And we've already learned this one. Any force, the unit for force is capital N. It's called a Newton, named in honor of Sir Isaac Newton. So it's a pretty easy formula. It's just got 3 different pieces to it. We'll do some examples in a bit. Okay. A second formula I want to show you then is how much energy something has. And I want to point something out. We've already learned this formula here. Work is a change in energy, right? In order to do work, you change your energy. But what was the formula for work? Wasn't work equal to a force times a distance? Okay. But isn't work also equal to energy? So if we start to kind of link some of these things together, this little bit right here, m times g, that is a force, right? But if you take a force and times it by a distance, that's equal to work, but work is energy. And that's why right here we've made a new formula, only rather than using D for distance, we've changed the letter to H. H stands for height. Because really, if things are going to fall, because that's what we're talking about, right? Gravity causing things to fall, rather than using D for distance, we use H for height because I guarantee you they're going downwards. So we use H instead as a new letter. So this is our new formula. It's basically force, mass times gravity, by distance, which is a height, that gives you a work, but that work we're going to specifically call a gravitational energy. All right, so two new formulas. Let's practice a few. Let's say that your locker has a shelf 1.8 meters above the floor. Your science textbook has a mass of 1.2 kilograms. Let's figure out how much potential energy it has. So imagine that like this is a picture of, I don't know, your locker. And here's the top shelf up here. And on the top shelf is a textbook. And this textbook is about to fall. Like it's tipping off the edge and it's about to fall. Can you guys agree that like it has energy just waiting there, waiting to be used? Okay? It's precariously perched, right? We want to calculate how much energy does it have due to gravity. Because that's the only reason it's going to fall is because of gravity, right? So the formula is we take its mass, we times by gravity, and we times by how much height it's going to fall by. Why does mass matter? Well, if the textbook was, rather than being a textbook, again, if it was a bowling ball, wouldn't you agree? Isn't that going to hurt you more? Right? So mass matters. So we should times by the 1.2 kilograms. We're also going to want to times by how much it's going to accelerate due to gravity by, right? And this number, it's called a constant. This G value, unless we're not on Earth, is always 9.81. Tomorrow, we're actually going to try to calculate that it is 9.81. That's our hope. We're going to do that with the falling object. So on Earth, we believe things fall at 9.81. And how far did it fall? 1.8 meters. So just got to multiply some numbers by each other. 1.2 times 9.81 times 1.8. My calculator spit out this number here. 21.1896. Not good enough yet. Okay. I know math is going to be a big part of what we use here, but in order for this to be physics, we need to do two more things. First thing we need to do is we need to round it properly. Based on the precision, this has 2 digits, this has 2 digits. This has way too many digits. So round it to 2 digits, call it 21. Still not really good enough though. 21 is just a number. We need it to be like a measurement of something. Energy is what we're trying to measure. What's the unit of measurement for energy? Joules. Capital J in honor of James Joule. There, that's an appropriate answer now. So, that makes sense? All right, so let's try some more examples then. Here, I'm going to tell you that you used 565 joules of energy to move a 12 kilogram box up a flight of stairs. Let's figure out how high the flight of stairs is. We're using the same formula, only now we have to use algebra to rearrange it. And again, that triangle method, although the triangle method works well for formulas like A equals V over T, it really does not work well at all with this formula of mg delta H. Like it just doesn't fit anymore. So we need to use some other algebra strategy. But let's just try plugging in some numbers here. Don't we know the energy due to gravity? Didn't it say how much energy was kind of being used here? So we have that number. It's 565 right here. And mass, don't we have the mass number? That's 12. And G for gravity. I mean, unless we aren't on Earth, it's 9.81. That's how much gravity affects things on Earth. What we don't know is our change in height. So we have to find a way to like algebraically rearrange this. Let me show you 2 ways that kids like to do this. And you can kind of pick whichever one you like. Here's the first one. I'll use a different color just to like differentiate the two. Some kids would like to do this. They go 565 and then they go 12 times 9.81. They go, okay, 12 times 9.81. And they discover that right here, these two numbers, if you multiply them, are 117.72. And then, once they put these two numbers together, then they divide both sides by 117.72. And by doing that, that kind of cancels them away and it gives them a change in height. Perfectly fine. If you like doing that, go for it. I got this answer here when I was done. 4.7995, and the number just keeps going for forever, with 2 digits worth, because the 12 is only 2 digits, right? This number should be rounded to 4.8, and height is measured in meters. So that's one way of doing it. Some kids, they like to do the algebra before they do all the math. And so here's an alternate way of solving things. If this makes sense, I'm going to go this way now instead. What some kids like to do is they like to get h by itself without putting these numbers together, and they realize that they just need to divide by 12 and divide by 9.81. So if this makes sense to you, they kind of rearrange it and they say the answer is 565 divided by 12 and 9.81. And they kind of put both of these numbers on like the bottom of a fraction over here. And like if that makes sense to you, you can do that too. The only thing I have to warn you of is that make sure that you like maybe put this in brackets when you use your calculator. But you can do like all in one big swoop, like all in one section if you like. Either way, you should get the same number. Okay. That's more of a math lesson than a physics lesson, and so if you need help on the algebra, let me know. I will help you on the algebra part. Okay. But unfortunately, hopefully you guys will agree though that the triangle will not work anymore. It can't, because now there's 3 variables plus this one over here. So, any questions so far? Okay. It's Monday morning. Of course there's no questions. Okay, let's talk about another form of energy then. When we go to the roof tomorrow and we drop something off the roof, it has potential when it's up on top of the roof, right? But as soon as it gets let go, it's going to start to move, and that is known as kinetic energy. Anything that is in motion has movement energy, right? And so the amount of kinetic energy really depends on 2 things: how fast it's going and how heavy it is. Right? It's going to have a lot of energy if it's a bowling ball, right? Why? Well, because it's really big. But it's another way you could have energy is, what if it was going really fast? This is the principle basically behind why guns are so dangerous. It's you, and I throw it at you, it's not really that dangerous in the grand scheme of things. Not that I should throw things at you, right? But if I shoot a bullet out of a gun, it has a lot of speed. Does that make sense? And so that's why it's dangerous, because it has a lot of energy due to that. So you can either have speed or mass, or maybe both, by the way. A car crash is very devastating because the cars that are hitting each other are very heavy, and if they're going highway speeds, you can kind of see how, like, if you have both of these things, you have a lot of energy, and that energy can cause problems when you like crash. So, anyways, here's the formula. 2 variables again. The formula is 1/2 of mv squared. Okay, a couple of things. There's a constant of 1/2 in here. It's always the number 1/2. You always have to cut things in half. And this velocity, the speed that you're traveling, you always have to square the number. So it's really like 1/2 times m times v times a second v. You really have to, whatever the speed is, you times it twice. That's the formula here. I want to point something out here. This formula is somewhat similar to this formula here. D equals VFT minus 1/2, what is it, AT squared. You guys recall this formula here? It's very similar to it if we remove this part and maybe the negative sign right here. Do you see how you have a number that's got a 1/2 in front? You've got a value here. In one case it was A, in this case it's M. And you have a number that's squared. Only last time it was T, now it's velocity. It's got a very similar feel to it. Okay. The only difference is that whole VFT gone. Let's try some examples. Say you got a car. The car is 1,500 kilograms and it moves 14 meters per second. Let's figure out its energy. Why does it have energy? Because it's moving. So we want to use a different little letter in the corner here, though. We use the letter K now, just to make sure that we're clear that this is a car that's moving, not a car that is about to fall. If it's about to fall, use a G in the corner. But it's moving. So the formula is 1/2 mv squared. And it just kind of looks like this. It's 1/2 times m, 1,500, times its velocity, 14 squared. Now, similar to like the previous formulas, like this whole triangle thing, it's really not going to work. The good news is on this method right here, I just need to time some numbers together. So 1/2 times by 1,500 times by 14 times by 14, or square it, either way. Here's what I got. 147,000. This is not a good number to write down. There's a couple of missing parts to it. First of all, anytime we end with zeros like this, it's a little bit ambiguous as to like how precise we measured this thing to. It could have been measured to the ones, tens, hundreds, or thousands. So it's not ideal. This number right here, by the way, also could have been rounded. I don't know that the car was exactly 1,500 kilograms. It could have been 1,497 rounded up. It could have been 1,450 rounded up. I have no idea exactly how this thing was rounded. But like, I know that this thing right here, has 2 significant digits. That 14 meters per second really limits me to 2 digits. So when I'm done, if I want to round this properly, here's one of the best ways of writing it. 1.5 E 5 joules. This is a good way of writing it, because it now guarantees that I only have 2 different digits here. And the reason why it's E5 is I had to move the decimal place over 1, 2, 3, 4, 5 times. Uncertainty of what the heck these zeros here and these zeros here mean by writing it that way. So that's a lot of energy, by the way, which makes sense though, because it was a car. Right? I mean, not that I want you to, but if you were to get hit by a car, like, it's not going to feel good because there's so much energy in the car, and that energy is going to get transferred to you, and our bones can't really handle that much energy and stress and fracture, right? Which is why they break. Okay, let's try another one here. A baseball has a mass of 145 grams. It's been thrown with a velocity of 26 meters per second. Let's find its kinetic energy. Now, I want to show you a mistake. Don't do this right now, but here's what some kids would do. They go, okay, 1/2 of m by 145 v squared. They just type it in like this, 0.5 half of 145 times 26 squared, and they get this number here, 49010. That's actually wrong. I mean, even if I were to put joules on it and like make it 4.9 E4 joules and do sig digs, that's actually still wrong. Does anybody know what I did wrong on this one here? Yeah. Yeah, the standard unit has to be in kilograms. So this doesn't happen a lot, but be careful, because if you're measuring something in grams, not kilograms, we have to change that mass value. So grams to kilograms means you need to know all of those, like, that's that staircase kind of ladder, you know, the one that goes like this maybe, where there's like millimeters and centimeters and kilometers and deca and deci. Like, you need to know how that works. So to make something into kilograms, a kilo is times 10 to the 3, which is 1,000. So if you want to go from grams to kilograms, we have to divide by 1,000. So it's actually 0.145 kilograms. Okay. That's the only reason why I've got this example for you, is just to make sure that you don't forget to convert this into kilograms. I mean, once you got that, this one's actually pretty straightforward. There's no algebra really to it. You just have to make sure you convert it properly. So I got this number now, 49.01. So all I got to do is just finish the question off now. I need 3 digits or 2 digits. Okay, so 2. And the unit for energy is a joule, 49 joules. To get hit by a baseball. But in comparison, which is worse, getting hit by the car or the baseball? Which, like, doesn't that clearly make sense? Okay, let's try one more example. No, I think this is my last example. I just have a slide afterwards. Let's calculate the speed of a hockey puck. Okay. I like this photo, by the way. One of the reasons I like this photo is that I can help kind of explain forces and energies together. You guys can see how, like, Stamkos in this picture here, like, he's got some pretty major flex on that hockey stick, right? That flex is actually a good example of a force. He is clearly applying a force by torquing his hockey stick right here. And so there is force being applied. Hopefully you agree with that, right? And that force is going to get applied over a distance. Where is the distance, though, that this force is going to get applied over? Anybody know? From about here to about, I'm going to guess right about here. That's going to be the distance that the force is applied over, because that is the amount of time, or that's the distance where the stick is to this direction right here, that way. But there's definitely going to be a distance and a force, and it means that he is doing work. But what is work equivalent to? Work is equivalent to, is he going to be giving the puck? Very specifically, he's going to be giving it kinetic energy, causing it to go flinging away. Very similar to the slingshot. Okay? So the formula we're going to use is that your kinetic energy is equal to 1/2 of mv squared. The difference here is that this time we're not solving for kinetic energy. Hang on, I'm going to erase where I put that. I need more room for this one. So the formula is EK equals 1/2 mv squared, but this time we're trying to figure out how fast the puck is going. So I'll start plugging in some numbers. 73 joules goes right here. The 1/2 goes right there. And I do know the mass number. The mass number is 0.21, and it's in kilograms already, so we're good. What I don't know is v squared. So let me show you a couple of different algebra ways that you can solve for v squared. Okay. The first one would be similar to what I did before. Why don't you take 1/2 and 0.21? Why don't we times them together? All right, let's put the 0.5, half of 0.21 gives you this number, 0.105 times v squared. Okay, so these two numbers are now one number, but it's being multiplied. How do you undo multiply? Divide. So I'll divide both sides by that number there. So 73 divided by 0.105 now gives me this number. Oh, this is gross. 695.2380952, and that equals. How do you undo a square? Square root. So then the last step would be to square root both sides. And since I'm not done my work, I really shouldn't round this number yet. Okay? Because of the fact that this number is not like my final answer, I really shouldn't round until I'm finally done. So if I take that whole answer and square root it, I get to this. I get 26.367 or so. And then maybe now I will round. And I get to round to 2 significant digits. So 2 digits makes it the number 26. And that would be meters per second. that's one way of doing the algebra. And if you like doing that, by all means, do it step by step by step. Nothing wrong with that. Okay. What I would like to in a second, though, is encourage you guys to maybe try my next method, which is to do it all at once. Okay. If you're going to go on in physics, we're going to use a lot of different formulas. Okay. Ask a Physics 30 kid to see their formula sheet. There's like 100 formulas on there. And doing it like little bit by little bit by little bit, by like timesing these numbers, and then dividing, and then square rooting. Like, it's tedious to do it like little bits, okay? So if you can kind of see how to do it all in one step, it's helpful. So I'll do it a second time here. The answer should still give me 26, but I'm going to do it all in one big swoop. How do you get rid of the number? Well, to get rid of 1 divided by 2, you really need to times by 2, but I'm not going to actually calculate it. I'm just going to put it times 2, right? And then I'm going to get rid of the number 0.21 by dividing by 0.21. And in order to get rid of v squared, I have to square root. And so some kids, they find it more useful to do this. They say that v times 73 all over 0.21. And they just do it all in one step. Okay, and if you can see that, I think there's an advantage to that. You don't have to. But this should get you the same thing. Okay. Let me redo my steps just in case that was a little bit too fast. I'll erase it and try it one more time here. So what were my numbers again? This was 73. This was 1/2. This was 0.21, and that was v squared. So new color, I guess. How do you get rid of 1/2? Well, you times by 2. If you times 1/2 by 2, that kind of cancels. And how do you get rid of timesing by 0.21? You divide by 0.21. That gets rid of this. And then how do you get rid of a v squared? You square root. That means that whatever this is right here, in a one-step calculation, that's your velocity. And it should give us 26 again, if we round it. So. Does that make sense? Okay, one more thought before I get to my last slide. You do need practice on this, okay? It's one thing for me to show you a few examples and you nod your head and you go, yeah, that made sense, Chris, right? I'll often tell my kids, I think there's 3 levels of people's understanding. Level 1 should really be level 0. It's where you don't actually understand. And if I've been talking for the last hour and you're like, I didn't get it, that's level 0, where it's like, it doesn't actually make sense yet. If that's you, we need to talk more, okay? Then there's level 1, where you can watch me do it, and you go, okay, yeah, that made sense. I can follow you, right? That's good. The next level would be where you can try doing it yourself a little bit, and you can kind of do it yourself, but you need to ask for help. The final level, kind of the third level, level 3 then, is where you can do it by yourself without needing help anymore. And that's what I want to help get you guys to, that point where you don't even need me to look it over anymore because you've got it. Right? That's what we're building towards. So anyways, my point was we need some practice now. Well, here's my last slide. It's more of a theory slide. We've been talking about work equaling energy, right? Work and energy are inextricably linked to each other. Work makes things have energy or makes them lose energy. I want to talk about a question off of your lab, the one that's due tomorrow. One of the questions on the lab asks you, where was work done on the Hot Wheels lab? There's actually 2 marks. Work was done to get the car up to speed, right? By making the car go faster, we did work. But work also removed energy from the object. Work is also friction, slowing it back down again, right? So we know that work can actually make things go faster or slower. It really does both, okay? I wanted to then talk about that first bullet there then. Negative work then is what would slow something down, okay? Positive work is accelerating and speeding it up. Negative work would be to slow it down. Hey, Kevin. So, it's Monday morning. We've already determined, actually, that like they're a little non-responsive, so we're going to get there. It's Monday morning. Yeah. Work. Yeah, work. We're almost in our lesson here. Okay, so last bullet here then. Let's just do an analogy here. Imagine that you're a baseball catcher, right? Someone throws a ball to you and you catch it. Does it make sense that the ball was going forward, right? Because I throw the ball, it's going that way, right? Here, let's actually just try an example here. Gustavo, you can catch, right? Okay, I'm going to throw this forward. Ready? You ready? What sort of work did I do? I did positive work. It's positive because I sent it that way and I sped it up. What sort of work did Gustavo do? Negative work, because by catching it, he slowed it down. Does that make sense? Throw it back again. Ugh. Good throw, right? Now, for those of you guys who play sports, do you guys know the idea of like cradling? Like when the ball comes in, you kind of like cradle it a little bit, or like when you hit a volleyball, you kind of like cushion it a little bit with your arms. Does that make sense? Those sort of concepts. That would be what's another good example? Like in hockey, where you receive a pass, you cradle the puck a little bit by moving your stick back with it. That is doing negative work because it happened over a distance. There's a little bit of a distance in which you need to like bring it into your body. Does that make sense? Like a baseball catcher doesn't just hold his hand like this. He like brings his hand back as he catches it, right? That's negative work. And the reason why it's work though is that it happened over a distance because your glove moves back. Okay. So anyways, that's my last concept is don't forget about how you can have positive and negative. Positive would speed it up. Negative would slow it down. Okay, I'm done my lecture for the day. Any questions? Not that I'm expecting to get a ton on Monday morning, but did it kind of make sense? As good as Monday morning can be? Okay, so here's what we need to do then. We've got a couple of tasks now to help you guys build your skills, because me just talking at you isn't good enough, right? I need you guys to practice. Option 1, work on your assignment. Little by little by little, there's some practice questions there. Work on that. Option 2, we did a lab last week on the Hot Wheels car. It's due, in finger quotes, tomorrow. Okay. So try to finish that today or tomorrow. I will give it back to you and let you make it perfect. If it's not 100%, you can make it 100%. Okay. And then tomorrow we're going to add a new lab. We're going to come to class. Okay. We're going to do a couple of measurements, and then we're going to go outside, and Brady's going to drop a few things off the roof for us. You're going to want to have a cell phone so that you can record how long it takes. And that should take hopefully no more than 10 to 15 minutes, I'm guessing. And then we'll do some practice on math on those. So on Thursday, you're getting a quiz. It's not meant to be evaluative. It's meant to be diagnostic to figure out whether or not you're getting this. Okay? This topic on energy is on our quiz. The lesson we do on Wednesday is not, by the way. So, sound good? Okay. Guys, you have about 20 minutes left. You're free to go somewhere else in the building if you want, but use your time well, okay? Okay, I'm done. Absolutely. Yeah, give me one sec here just to get organized.